I want to welcome you to Science Head's very first online star party. Our focus tonight are the gas giants of our solar system, Jupiter and Saturn. Together, we're going to learn a lot about these planets and their moons. During this event, we would appreciate if you'd keep your microphone muted so everyone can hear us, but you are welcome to enter your questions at any time into the GoToMeeting chat window. We'll do our best to answer all of your questions either during or after the event. And students, please let us know what grade you're in. Before you start, I want to tell you a bit about us. Science Heads is a 501c3 nonprofit organization whose mission is to promote and support STEM education. We host educational events at school and public venues. Our volunteers love science, technology, engineering, and math. If you do too, I invite you to check out our website. Now, the NASA Solar System Ambassador Program that I mentioned is run by the Jet Propulsion Laboratory. The program trains volunteers to inform the public about NASA missions and related science. I'm just one of the more than 600 ambassadors who volunteer for this program. Tonight, I'm pleased to be joined by two other ambassadors, Dr. Michal Peri and Ruth Kurisu. Michal has a master's and PhD in astronomy from the California Institute of Technology. Before retiring, she designed spectroscopy instrumentation for the Palomar Observatory. Now, she's focused on demystifying science and math for children and adults via outreach events like tonight's Star Party. Ruth received her Bachelor's of Science and MBA from UCLA. She's an analytical chemist, a nuclear quality engineer, and an entrepreneur. Her company, Saturn, provided components for the International Space Station. Ruth will be reading your questions tonight and helping us answer them. And again, my name is Richard Stember. I have a bachelor's degree in chemistry. I'm an entrepreneur and an avid amateur astronomer. I love sharing astronomy with the public. And back in 2014, I started Science Head so I could do just that. As I mentioned, tonight's star party is focused on Jupiter and Saturn. Behind me, you can see the computers which I'll be using to monitor the remote telescopes we're using tonight. I'll be sharing those screens with you and explaining how this all works. But first, let's learn more about these giant planets.
So, Richard, can you give me the next slide, please?
Absolutely, Michal. Here we go. And this brings up the question I was going to ask you, Michal. And that is, we generally know what a planet is, but obviously scientists have a very exact definition. So what do we mean by a planet? What is a planet?
Well, actually, I'd like to just, okay. So the word planet comes to us from the ancient Greek term, which I'm not going to try and pronounce, but it's kind of pronounced like planets, meaning wanderer. And that's because when ancient people looked up in the sky, they saw that most of the stars are fixed in their places, and they'd see the same constellations night after night and year after year. But there were a certain number of lights in the sky, star-like objects, that moved around relative to the positions of the fixed stars. And there were 7 of these objects that moved around that were wanderers. 2 of them were the sun and the moon. And those are different from all the other objects in the sky because the sun and the moon, they don't look like points of light, but they're great big things. But then there were 5 more that were just points of light, but unlike all the other stars, they moved around. And those are the 5 planets that were visible to the naked, that are visible to the naked eye and have been known since prehistory: Mercury, Venus, Mars, Jupiter, and Saturn. We'll be looking at the last 2 of those tonight, Jupiter and Saturn. Next slide, please. So you may have noticed that that list didn't include 2 other planets, Uranus and Neptune, that have been discovered in modern times after the invention of the telescope. That's because they are too dim to be seen by the naked eye. Now, most of us, if you're over a certain age, probably learned that the sun had 9 planets in its solar system: Mercury, Venus, Earth, Moon, Jupiter, Saturn, Uranus, Neptune. I missed one. What did I miss? And Pluto. Did I miss one? No, I think I got them all. Um, but Pluto is no longer considered a planet. And I know that some people are really unhappy about it, but that's because we wanted to have a consistent definition for what a planet is. We didn't want to have any special cases. So in 2006, uh, Richard, go back to the other slide, please. It flipped on us.
Oh.
Nope, that forward one. Nope, nope, nope. The definition of the planet, please. Yeah, great. Nope, one more forward, please. Yes, that one. Stay there. So in 2006, the International Astronomical Union, IAU, voted in favor of the following definition of a planet. A planet is a celestial body that, one, is in orbit around the sun, two, has enough mass for its gravity, its self-gravity, to pull it into a spherical shape. So it basically can just overcome the other forces and pull itself into a nice roundish shape. And third, has cleared the neighborhood of its orbit of other debris. It sucked all that debris into itself. So those are the three factors that an astronomical body has to satisfy in order to be a planet. And what happened with Pluto was that while it is a spherical shape, it just isn't big enough to have cleared the neighborhood around its orbit. And so it has a lot of other space junk in its orbit. And the other thing is if we change the definition to still include Pluto, there's other objects. Maybe some of you have heard of the Oort cloud, which is a giant band of objects way far away from the sun. But there's like 200 other objects out there that are kind of like Pluto that we think are big enough to have pulled themselves into a sphere, but haven't cleared out their orbit. And it really wouldn't be fair to let Pluto be a planet, but not let all those other objects be a planet. And believe me, you don't want to have 200 more planets to memorize the name of them in science class. So that's why Jupiter got dropped out. I'm sorry, that's why Pluto got dropped out. And that's why we now say that the sun has 8 planets. Next slide, please.
So, Michal, I've got a question for you. We're going to be viewing Jupiter and Saturn tonight, and they're both referred to as gas giants. So, what does that mean? Why do we call them gas giants?
Well, a lot of you have seen pictures like the one that's on your screen now of the planets in our solar system. And it looks like, wow, we've got all these 8 planets and they're all kind of about the same size and they're all kind of about the same size as the sun and they're all kind of spaced about the same. And that picture is really, really misleading because first of all, the sun is hugely bigger than any of the planets and they're not all spaced like that. The rocky planets in the inside, that's Mercury, Venus, Earth, and Mars, are a whole lot smaller and, as you might guess from their name, they have a rocky surface like we do here on Earth. Yeah, we've got water and we've got rock, but there's a clear demarcation between the surface of the Earth and our atmosphere. The outer planets, Jupiter, Saturn, Uranus, and Neptune, aren't like that. They have great, big, thick, heavy atmospheres, and it's kind of hard to tell where their atmosphere ends, and there isn't really a nice, easily defined surface the way there is here on Earth. They're also called giant planets because they are so much bigger than the rocky planets. For instance, Jupiter is, I believe, 1,000 times the mass of Earth. That's huge, a whole lot bigger, and yet it's still only 1%. That is 1/100th times the mass of the sun. So here we've got a really nice picture of Jupiter, which we call the king of the planets because it is so much bigger than any of the other planets. So Jupiter is the fifth planet from the sun. It's 43 light minutes from Earth, which means that if there's a spacecraft around Jupiter, in orbit around Jupiter, like the Juno spacecraft you might have heard about recently, it takes 43 minutes for light or information to get from Earth to that satellite. And it also takes 43 minutes for any images that it takes, any pictures that it takes to get beamed back here to Earth. Jupiter, because it's a lot further out from the sun than the Earth is, takes just shy of 12 Earth years to go once around its orbit. So if there's any 12-year-old kids out there, just a little bit of 12, Jupiter's almost in the exact same place in its orbit around the sun as it was when you were born. On the other hand, Jupiter spins around on its axis really fast. One Jupiter day takes 10 hours compared to one Earth day. That's the time the Earth takes to spin around on its axis. One Earth day is 24 hours. So Jupiter spins a lot faster than the Earth. Jupiter right now has 79 known moons. And you might see in the picture, the little inset picture on the slide, Jupiter's the bigger spot with the kind of stripies on it. And then there's 4 other bright moons, which we'll hear more about in a second. The other really well-known characteristics of Jupiter are the great red spot, which you see in the lower right of the surface of the planet. And it's kind of salmon red now. It used to actually be darker, more like a brick red. And scientists don't know why it's changing, but it's been changing. That spot's been there for over 400 years, but the last few decades it's been fading a little bit. And then in the upper right pictures, you see the 4 brightest moons. And those have been known since Galileo invented the very first telescope. He was an Italian scientist. He invented the very first telescope in the early 1600s. And one of the first things he looked at was Jupiter, and he saw that it's got 4 little spots around it. Richard, could you give me the next slide? So those 4 little spots, which are not all lined up like they are in this picture, they're kind of spaced out like you saw in the previous picture. Those 4 spots we call Jupiter's Galilean moons after Galileo, who discovered them. And they are Ganymede, which is the biggest one, Callisto, Europa, and Io. And what is amazing is that each of those 4 moons is super different from each other. Io, the little one at the bottom, maybe it's pronounced Io. I never figured that out. Anyway, you see how it has kind of some dark spots on them that maybe look like blemishes? Those are actually gigantic volcanoes that are spewing stuff into space. And Ganymede and Callisto, they are completely covered. Actually, it's Europa and Ganymede are completely covered in ice. In fact, they think that that Europa has an ice covered, like the crust, the outside is like a skin of ice over a big, deep ocean. And that's actually, they think, a very interesting place to study because we know that where you have energy, like it still gets some sunlight, and rock on its core, and then an ocean around it, that those are some of the conditions that might maybe be conditions for life to form. So more on that later.
Hey, Michal.
Richard, can,
Just wanted to mention we're going to get our first live image in less than 15 minutes. Would now be a good time to see if there's any questions from our guests?
Yeah, are there any questions about Jupiter?
Well, we do have a comment here. Somebody asks if you can make the slides full screen.
They can actually do that from their end if they click on the expand button in the upper right-hand corner of their GoToMeeting. I think that will help.
So does anybody have any questions on Jupiter? Because otherwise I'm going to
Yes.
tell you about Saturn.
Yes, I have one. This is George. I've always wondered why we have gas planets. Why is there such a big difference between the rocky planets and the gas planets? Why are they gas?
That is a really good question, because what you would have expected is you would have expected each planet to kind of gobble up all the gas. When the solar system was forming, you kind of expected that each planet would gobble up all the gas in the area of its orbit, and that the sizes maybe might be more evenly distributed. And what they think is they think that Jupiter actually formed not outside in the outer part of the solar system where it is today, but when Jupiter formed, it was actually closer into the sun. And so it gobbled up a lot of gas and dust that might otherwise have gone into forming some of the other inner planets. And that's something, but they don't really know what it might have been. Maybe the gravity from a passing by star early in the formation of our solar system pulled Jupiter and made it start wandering around into the orbit, kind of away from the sun. Actually, they think first it passed closer into the sun and then kind of slingshotted out, and that something else interacted with the solar system gravitationally, maybe a second passing by star, and that's what made it Jupiter go into the orbit where it is now. So it's kind of Jupiter's fault that the inner planets aren't bigger and have bigger, heavier atmospheres. And also the reason that Jupiter is so much disproportionately larger than even any of the other gas giants. It's a fascinating theory that's based on discoveries from the Voyager and Juno missions that we sent out to Jupiter.
Michal, I have a question here. What makes the color of the planet Jupiter?
Oh boy, that is largely related to chemicals in its atmosphere. And if you look at the picture that's on the screen right now, you see that great red storm, the great red spot, which is a giant storm. It's so big that you could drop 4 Earths side by side into that storm. But then you can also see kind of down below the storm, there's 2 kind of wider spots. And those are white storms in kind of maybe mauve colored band of atmosphere. And then in between those 2 and the red spot, there's sort of maybe mauve-y storm in kind of a light gray band of atmosphere. And all those different bands of atmosphere are all caused by different chemicals that are in bands of the atmosphere that are, if you think about the jet stream here on Earth, or maybe some of you guys heard about the dust storm that came from the Sahara Desert and went all the way around the ocean across the Pacific and, across the Atlantic, and was causing really spectacular sunsets earlier this summer on the American East Coast. So it could be that there's dust or other chemicals high up in those bands. Any other questions about Jupiter? Because I'd really like to have a chance to talk about, to let Richard tell us about the telescope a little bit in this segment, and also at some point tell you guys about Saturn.
All right, very good, Michal. It's not something that most people know how to do, but there's actually telescopes around the world that people can remotely control. So you may be wondering how we're looking at night sky objects so early in the day here in California. Well, we're using telescopes that are in the Canary Islands off the west coast of Africa, and I've got that circled on the slide that I'm sharing with you right now. The Canary Islands are islands that are under the purview of Spain. It's a very popular vacation spot. and there are dozens of telescopes installed on one of the islands there. And you see a panoramic picture of many of those telescopes housed in observatory domes. On the left there, lower left picture, we can see the telescope that we're actually using. I'll tell you a bit about this telescope in just a minute. But notice in that panoramic shot, there's a tall peak on the right-hand side. That is an extinct volcano. That tower is about 12,000 feet high. We're very high up here with these telescopes, and which gets us above the atmosphere, reduces distortion, and this organization called SLU makes it possible for people who purchase a subscription to actually control the telescopes and schedule viewing time with them. The telescope itself looks like this. This is not the actual telescope, but a very similar one. It's a 14-inch diameter Schmidt-Cassegrain telescope. And Schmidt-Cassegrains are very unique in that they have a series of mirrors. You can see the light diagram there with a picture of the Big Dipper at the top there. The light enters from the top. It bounces off a large convex primary mirror and then back up to a smaller secondary mirror, and then exits out a hole that's actually cut in the primary mirror. And what you get is an image which is upside down, which doesn't really bother astronomers much. There is no up or down in space, but typically connected to that hole would be a camera, and that's what we're using tonight.
Richard, before you go on, can you just tell us again on that telescope how big it would be, like if there was a person standing next to it?
Sure. So that's a 14-inch diameter telescope. Imagine if you had a camera like a DSLR that was 14 inches wide. The lenses were 14 inches wide. It would weigh a ton. Well, not literally a ton. It would weigh about 100 pounds, and that's what this telescope weighs. It takes 2 people to safely pick this telescope up and put it on its mount, but it is very large. It's about from a typical person's waist up to the top of their head in length.
Okay, so the kind of cylinder thing that you're seeing there is maybe the size and length of a man's upper half of his body.
That's a good comparison, yes. Mm-hmm. And it's mounted permanently inside a dome there on this island, and connected to it is a large format camera like the one that's pictured here, and a series of filters in a filter wheel. And the software that controls the telescope will automatically capture the images at the appropriate time. And I see that we've got about 5 minutes before our first image starts appearing. I'll share that with you in a moment. But I did want to also, if it's okay, Michal, talk a little bit about how you plan this all out. What do we have to do to know what we're going to point the telescope at and make sure that we're pointing at a useful part of the sky? So I'm going to share with you a piece of software that I use called K-Stars. And K-Stars is an application that's actually free. You can download, and it is a planetarium, what we call planetarium software, and it gives us a representation of what the telescope is going to see, or what's in the sky at least, at the time that we're using it. And here you can see above the southern horizon, we can see the planets Saturn and Jupiter, as well as Neptune. The moon and Mars are all above the horizon at this particular location at this particular time. It's a little after midnight there in the Canary Islands. This software is free. I'll give you the link for it a little bit later in today's presentation. And it's a lot of fun to play with. With our other telescope.
It's a little bit like Google Sky that some of our guests might have downloaded onto their cell phones, and you can just hold it up in the sky. Well, Google Sky is the one on the cell phone. You can hold it up into the sky, and it can show you the names of the stars or planets like that. And it's just one of a number of different software applications that you can get for your computer or for your cell phone that can help you enjoy astronomy. And Richard, would this be a good time to tell them about Eyes on the Sky, which is a NASA application that they can use?
Sure.
Or do you want to do that after the observing?
Well, we got a couple of minutes here before we start getting our first image. The NASA
Okay,
Eyes on the
just make
Solar
sure you just make sure you leave me a minute to tell them what we're going to see on Jupiter.
Absolutely. The NASA Eyes on the Solar System software is another free package. This one was designed by the JPL people, programmers up in outside of Pasadena. And it's a simulation of all of the objects in our solar system, all the moons, the planets, comets, asteroids, larger asteroids, all of the NASA spacecraft. You can take a virtual tour of the solar system. And to download the software, just Google Eyes on the Solar System. Again, it's free, and it's a lot of fun to play with. It's a great educational tool for students. So turning it back to you, Michal, what are we going to see when we take a look at Jupiter tonight?
Can you give me back that nice slide of Jupiter that we have?
Sure.
So when we look at Jupiter, this is a picture that was taken, I believe, from the Hubble Space Telescope. And you can see a lot of detail. You can even kind of see all inside the individual storm bands. You can see like swirls and stuff like that. What we're going to see is more like the picture in the upper right with the picture of the inset. And we're going to see Jupiter. If we look closely, we should be able to see the bands in the atmosphere, some of the more prominent bands. And then we should also be able to see several of the moons of Jupiter. In fact, I believe that when we look tonight, one or more of the moons will actually be in front of the planet and casting a shadow down onto the planet. So be looking for the stripy bands in the atmosphere, the great red spot. Hopefully we'll be able to see that, and be looking for the four, I think we're going to see 3 of the 4 Galilean moons. Those are the ones that we showed you in the picture that Galileo discovered with his very first telescope in the 1600s. And be looking in case there's a shadow spot on Jupiter that is being made by one of the moons being between the planet and us, kind of making like a little bit of an eclipse on the moon.
So, Michal, we're getting.
Oh, is that our live image, Richard?
It is. This is this first image. I'm using a Canary 3, which is also a 14-inch wide field telescope, to show us the positions of the moons tonight. So you can see Jupiter's overexposed. That's expected, but you can see 4 of the moons all off to the right there. So that would
Oh.
Io, Callisto, and Europa, all lined up like that. And that's what Galileo saw when he pointed that telescope at Jupiter. And over a series of nights, he discovered that they were changing positions. They were moving, and that's what led him to believe that they were moons, and also supported the heliocentric theory of our solar system, that the sun is at the center of our solar system. Back then, most people thought that the Earth was at the center of the solar system.
At the time that Jupiter discovered that, that was considered a huge heresy because they thought that the sun was the center of the solar system, and the solar system was kind of there for us, and everything went around the sun except the moon that went around us, and that it was all there for us, and like we were so special. And Galileo discovered that there's things that don't go around the Earth, that don't go around us. And uh, he was actually excommunicated by the church for that heresy. But now that we know that he was actually correct and that there's lots of things out in space that don't just go around us.
Yeah, when he made that discovery that the Earth was not at the center of the solar system, it created quite a ruckus among the religious authorities. So we've got another 2.5 minutes before we gather our next image. It's going to be from Canary 4, which is another telescope on the island there. I'm going to switch over to that telescope right now. Now, there's other astronomers using it, so somebody is probably gathering an image. It'd be interesting to see what they're gathering. So let's switch over to Canary 4 and capture our live image. Now, earlier in the evening, Michal, I happened to notice another astronomer capturing Jupiter, and the great red spot was definitely visible. I think we're going to miss it, though. I think it may have rotated by this time, but I'll bring up that particular image so everyone can see what the great red spot looks like when you image it through a telescope like this. Oh, this is a nebula called the Dumbbell Nebula. Kind of looks like a dumbbell. You know, when we have our Life of the Stars star party, that's something we're going to talk a lot about, nebulas, and we may visit the Dumbbell Nebula at that time.
So actually, Richard, what you said about the great red spot might not be visible to us because the planet rotated away, and in real time when we gather our light image, that the great red spot the planet might have turned so that the great red spot is kind of behind the limb of the planet, is actually a really good reminder that Jupiter makes a complete turn 360 degrees around its axis every 10 hours.
That's incredible.
And so it goes from day to night to day. And it doesn't always keep its best face forward to us, but we're still going to see lots of really cool, interesting things.
So, Ruth, are there any other questions from our audience?
Well, I have a question. Could people live on Jupiter?
Oh, wow. That's a great question. When we talk about looking for life, we usually mean life as we know it. And all of the life that we know it here on Earth is based on kind of reactions, chemical reactions in water. Now, most of the life on Earth uses energy from the sun, but you might have heard about that there's life deep down in some of the deep ocean trenches and the crevices around the mid-ocean rifts that is getting its energy from kind of the interior of the planet. But even that life, even though it doesn't depend on energy from sunlight, is still depending on a water-based chemistry. And all the life that we know of, all the ways we can think of life, depends on this water-based chemistry. And Jupiter, we're going to see our first image. So exciting. Let me just finish this question real fast. Jupiter does not have a water-based chemistry in its atmosphere. And its atmosphere is made up of things like methane and ammonia that would be toxic to the kind of life that we know. But some of the moons of Jupiter, in particular Europa and also, there's several of the moons of these giant gas planets. So Europa and Callisto by Jupiter, and Saturn's giant moon Titan. All of those we think have a liquid ocean underneath a big heavy coating of ice, a big heavy surface ice crust, but we think it's possible that life might exist in those oceans. And we sure would like to find that out by NASA's planning a mission that would go out called the Europa Clipper that would actually go and drill a hole down through the ice on Europa and taste the waters and do chemical analyses of the waters on Europa to try and figure out whether life actually exists there. But I see this gorgeous image come up. Richard, tell us what we're seeing.
So we did catch the great red spot before it rotated past the limb. It surprised me here. And the seeing, as we like to say, is really good tonight. By seeing, I mean that there's very little distortion in the Earth's atmosphere. You know, the Hubble telescope is a larger telescope than this telescope is, but it's up in it's up in space. It's in orbit around the Earth, and of course, there's no atmosphere there to interfere. Down here on Earth, all of our telescopes are at the mercy of what the atmosphere is doing. And if there's a lot of turbulence and moisture in the air, it can degrade the image, but not tonight. In the Canary Islands, it's very dry right now. The temperature is very cool, and we're seeing some beautiful images right now. It's in black and white because the telescope collects actually 4 different images in different wavelengths or colors, and later on we'll combine them together to create a colorized version of the planet. But look, you can see quite a number of cloud bands. We see in the southern hemisphere, we see the great red spot, and if you look really closely, you may be able to see some other storms. Now, Michal, did you tell us what the can you tell us what the great red spot is?
The Great Red Spot is a giant storm. Think of like the biggest hurricane ever. So it's all swirly around in there, but it's really long lived. It's been there ever since Galileo first saw Jupiter. So that's, gosh, over 400 years ago. And the reason it's red is because it's just got a lot of reddish chemicals and like some high up dust high up in the atmosphere. And what we think it's doing is kind of like hurricanes or tornadoes on Earth. It's kind of like pulling stuff up from lower levels of the atmosphere up into the upper levels of the atmosphere. So you're kind of seeing from deeper down inside the planet, and that's why it's got the different color. And same thing with like that dark band that you see at the top. And then the lighter band, you can see it's not really straight. It kind of curves a little bit around that red spot. And that's just one extreme example of how these giant storms kind of bend the flows of the atmosphere, just like maybe you've seen on weather maps here on Earth that the Gulf Stream can have kind of loops and where it kind of goes up and down, and sometimes maybe it'll like loop down and bring us really cold weather, and we get one of these what do they call it when we get like the really, really cold weather in the wintertime?
You referring to an inversion or?
No. I know. Another example of it is like when we get the Pineapple Express and it brings us extra rain from Hawaii.
Yeah.
And that's like a ribbon of a lot of water vapor in Earth's atmosphere.
Mm-hmm.
Well, that's what we're kind of seeing with these bands are ribbons of different chemicals in Jupiter's atmosphere.
Well, we're switching over to Saturn now. The telescope, while it was collecting those or processing those images, slewed over to Saturn, which was not very far away, just a few arc minutes away, and we're getting a pretty good view of Saturn. Here we're collecting photons right now with our imager, and the rings are clearly visible, and I can see some cloud bands on Saturn as well. And I don't know, maybe your eyes are better than me. Can you see the Cassini division, Michal?
Oh boy. I need to look at it really closely.
Well, let
You
me
know,
switch over to the slide.
I don't think I quite do see the Cassini division.
Okay.
And I don't know.
Let me switch over
It's
to the
I
slide so people know what we're talking about. So,
yeah, let's go back to the slide of of Saturn because I kind of didn't get around to doing that part.
mhm.
So here's a picture of Saturn taken by the Hubble spacecraft. And what we see is we see the rings, and you kind of see how there's lighter rings, and then there's what looks like a black ring, and then there's some darker gray rings on the outside. And that black thing is actually a gap between the inner and outer rings. There's not just uh, like one simple ring, it's actually rings inside of rings that are all kind of separate. And what makes those divisions is moons that kind of clear out the path of their orbit inside the rings, just like we talked about how to be a planet, something's got to clear out its orbit in the path around the sun. And then you kind of see the shadow. So in this picture that we're seeing, the sun is in the kind of middle lower right. And then if you look back on the left side of the planet, we're seeing the shadow of the planet on the rings. And then in the inset up on the upper right, you see some of the biggest moons of Saturn. So what we're all looking for very, very carefully is to see if we can see that dark division in the moons of Saturn.
And the image
And
that just got collected, Michal, actually is
uh-huh.
now showing it. So let me switch over back to the telescope. This is a colorized image, and we see some definite colors there. And I can just barely see the Cassini division. It's a dark band right about here. I just drew a line which ends in it there.
Yeah, I actually see it more clearly on the other side of the rings.
Okay, yes,
Because
it's
I
over there
see
as
the
well.
brighter bands, and then I see the Cassini division, and then I see kind of, you might think it's haze, but it's actually not haze. It's actually the darker, it's actually the less reflective rings on the that are a little bit further out. And I also really like this image because I can see one of those bands in the atmosphere of Saturn, like we saw in Jupiter, kind of a little bit up above, a little bit up, like maybe
Right
two
about
thirds of the way up. Yeah, right there. That's a really nice picture of one of the atmospheric bands of Saturn.
right, right.
And like Jupiter, Saturn has those bands in its atmosphere, but it's not nearly as violent of a place as Jupiter. Um, we don't have any spots that seem to have stayed the same for hundreds of years, as much as we can tell.
Hmm.
And we have had some really nice close up images of Saturn by the Cassini mission that NASA sent out that examined Saturn and several of its moons and actually landed a probe, the Huygens probe, on Saturn's moon Titan.
Hmm.
Now, can we see any of the moons in this image? I'm not sure, Richard. I think maybe I might, but I'm not completely sure.
No, no, we cannot, and that's true of the Jupiter image as well because of the way the exposure is managed. It's hard. The moons are not very bright, so
Oh.
to get the moons and the planet, it'll wash out the planet. To get the details on the planet's upper atmosphere, we don't get enough light to capture the moons. So it's 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 what's referred to as the dynamic range of the camera itself. And in fact, you know, if you were looking through the telescope in person, you would see a somewhat better image in that respect. You would see both the moons and the detail because the human
Hmm.
eye actually has a wider linear dynamic range than cameras that we make.
The
So
human eye is so amazing, and we all know this, from our own experience that if you are sitting with someone in a fairly dim room and then there's a light maybe on a side table next to the sofa they're sitting on, with your eye you can see their face just fine, but if you tried to take a picture of that same scene, they're like the light would be totally washed out, the lamp would be totally washed out bright, and you might not be able to make out the person's face in the picture, but your eye has no trouble with it at all. And that's just something that the human eye and the human brain is so amazing, that our brain does all this processing, that we have to do a lot of post processing of the pictures from Hubble or the spacecraft images to get those really sharp images like we saw before, where you saw the planet and its moons.
Hey, Michal, I'm seeing some questions from our guests. Ruth, would you like to share some
Yes,
questions?
we have one here that probably for you, Richard. What level of magnification did Galileo have 400 years ago?
Wow, that's a really good question. Off the top of my head, I don't remember. His telescope was about 2 inches in diameter. It was also about 6 feet long. And I've actually been to Florence and went to the Galileo Museum there. And they have on display a variety of the telescopes that he used. The optics back then were incredibly primitive. In fact, when he looked at Saturn, to give you an idea, now we clearly saw rings. We could tell that they're rings. But when he looked at Saturn with his telescope, he described them as ears because he couldn't tell where the planet ended and the rings began. And he didn't even think they were rings. He didn't know what they were. He referred to them as ears. So the quality of the optics was very poor. The magnification was fairly high, but it produced quite a distorted image. So that's a really good question. If you make it to Italy, you go to Florence, be sure to go to the Galileo Museum there. And it's stocked, it's chock full of all sorts of scientific instruments, including many of the telescopes that Galileo used himself.
I will say that Galileo, the image that he saw through his first telescopes, were not even as good as what you can see with a decent pair of binoculars. And if you don't have a telescope, but you do have some, binoculars that maybe you use for bird watching or something, you can take those out in the night sky, and with the help of a program like the one Richard's using or Google Sky, you can point it at Jupiter and Saturn, and you will actually see a little disk. And if it's a real good clear night and your hands are steady and your eyes are good, you will probably see the ears on Saturn the way Galileo did.
And talking about binoculars, before I forget, there's a naked eye comet up in the sky that you can see right now. And I'm going to share a slide with you to give you some quick directions on how to see it. It's a pretty interesting object to see. If you've never seen a comet, get yourself up before the sun rises tomorrow. Here in California, the sun rises at a little bit before 6 a.m. If you have a clear view of the eastern horizon, you'll be able to see Comet Neowise. It's a naked eye object. You'll see it has a tail. With a pair of binoculars, you may see that it has 2 tails. So I just didn't want to forget to mention that before we wrap this up tonight. If you're elsewhere, for example, if you're one of our guests from Oklahoma, sun rises there at 6:23, so you can sleep a little bit later than we can here in California. But you do have to get up.
I do want to add on that, Richard, that it's going to be really hard to see if you're somewhere like right in the middle of Orange County or right in the middle of Oklahoma City, and where it's really like there's a lot of lights and a lot of light pollution in the sky. And you're going to have a much better view if you can get somewhere where the skies are really dark.
Yeah.
And it will, a little bit later on in the summer, it will also begin to be visible at sunset, after sunset.
That'll be
So,
after July 15th.
yeah.
It'll become visible after sunset. So a little bit more forgiving if you're not
Hmm.
an early riser. But
But
I'll
again,
post some information on our website about that.
yeah, it'll be posted on the Science Heads website. But again, if you really want to see something that's going to knock your socks off, you have to get somewhere where there's a really dark sky.
Mhm.
So maybe think about doing a camping trip out in the desert if you're in California. And I know that out in Oklahoma, there's some nice areas that aren't too densely populated. And that's actually something that I wanted to raise with our audience, that the darker the skies are, the better you can see. And that's part of the reason that we build telescopes in places like the Canary Islands, because there aren't big cities on those islands. So there's not very much light pollution. And some of you may have heard of the Palomar Observatory, which we have down here in Southern California, or even the Mount Wilson Observatory, which was built around the beginning of the 20th century. And in the early, I think Mount Wilson was built in like the 1920s. And back then, Los Angeles wasn't very big, and the skies, like to the east of Los Angeles, were pretty dark. But now we've built up so many communities out in the San Gabriel Mountains and all of the Inland Empire that there's a lot more light pollution in the sky, which makes it a lot harder for those observatories to observe faint objects. And so they still have scientific uses. They still have scientific purposes, but they get used more for studying brighter objects like the planets or like brighter things in the sky. And the really dark objects get studied by telescopes that are like out in the Hawaiian Islands, where there's less light pollution, and out in the Canary Islands. I did
Michal,
see,
we do have a question here from one of our audience members. I know you talked about the red spot a
Mhm.
little bit and the change in color. Our guest would like to know, has it changed in size over the years or has it stayed the same?
Yeah.
So it has pretty much stayed the same. It's kind of hard to define the boundaries of exactly what the size is, because it doesn't have like a real sharp boundary. If you think about like a picture of a hurricane here on Earth, and you've got the swirly pattern, but it's kind of hard to say where the swirly part ends in a hurricane. But it has pretty much stayed the same size. I think the variations are of order about 10% of the linear extent of it.
As I recall, it's about the size of two Earths, isn't it?
Yeah, in terms of two Earths side by side, or if you think about, since it's round, you could kind of fit four Earths inside the circle. So four smaller Earth circles inside the big circle of the giant red spot.
Mhm.
So diameter twice the diameter of the Earth,
Well, I see we're
but in
coming up
area.
to the end of the hour. Ruth, are there more questions?
There are no more questions in the chat box, but it might be interesting if we could tell our guests if any spacecraft have visited Saturn or its moons.
Oh, really? That's a good
Yes.
question. I got a slide on that. Michal, do you want to answer that?
Yeah, would you bring up the slide, please?
Mhm.
So these are some of them. These are the list of missions that NASA has sent out to the gas giants. And the years that are posted there are when they were active. So the very first spacecraft that we sent out to the outer reaches of the solar system, where the gas giants are Pioneer 10 and 11. And Pioneer 10 went by Jupiter and several of its moons. Pioneer 11, which was launched later the same year, its orbit was swung around and it kind of went used Jupiter as a slingshot. So it got close to Jupiter and then used it as a slingshot to go to the outer planets, Saturn, Uranus, and Neptune. And it's actually, I'm wrong about that. I was talking about Voyager. Uh, so anyway, Pioneer 10 and 11 went by Jupiter, and then Voyager 1 and 2. Voyager 1 was the one that went by the different moons, and Voyager 2 was the one that did the slingshot and went by Saturn, Uranus, and Neptune. And it is still the only mission that we've ever sent out to these outer planets, the outer gas giants, that has seen Uranus and Neptune. Of course, we know that there was a mission out to Pluto, and I'm blanking on the name of that one.
New Horizons.
New Horizons.
Thank you, Richard. Sometimes I have Swiss cheese for brains. So then the Galileo mission was a mission that was sent specifically to take close-up shots, and it was the very first mission that was ever put in orbit around Jupiter. And it was just designed to last, I believe, 5 years, but it actually lasted, as you can see, from 1989 out to 2003. Similarly, Cassini mission was sent out and put in orbit around Saturn and did flybys of several of Saturn's moons, including sending a lander, the Huygens lander, down to the surface of Titan. And then the most recent look that we've had is the most recently launched mission is Juno, that was launched in 2011, and it was sent out to orbit Jupiter and indeed sent a probe down into Jupiter's atmosphere. And then there's a really super exciting, because I'm interested personally in explorations about whether there might be life on other planets. So I'm super interested in this planned mission called the Europa Clipper, which is planned to launch in 2024, which, if you think about it, is really only a few years away. And it is going to go and take a close-up mission of the moon Europa and drop, the plan is for it to drop a probe down that would drill through the thick layer of ice down into Europa's ocean and release a probe that would go and explore the chemistry of that ocean. And it could be, I think it's got a reasonable chance of being the first discovery of life in anywhere in the universe other than planet Earth. So I'm just super, super excited for that mission. And sometimes, like, there's even news on it already, as you can see images of the plans for the mission. You can go on the nasa.gov webpage and nasa.gov/Europa Clipper and get information on that mission. So that's one I'm super, super, super excited about. So we just have another minute. Any other questions?
How far has Voyager gotten?
Oh, this is super cool. Voyager, both 1 and 2, are the farthest away objects, human-made objects from Earth, and they are both now outside the heliosphere, meaning outside the area of space that is dominated by the sun. In this image, you can see, this image actually doesn't show it very much. They are way past the orbit of Neptune and Pluto, and they are actually out in interstellar space now. And the reason we know that is because Voyager 2 in particular has an instrument on it that studies plasma, and it's been taking readings of the plasma out in space by where it is in space. and it has detected that it is not seeing any solar wind at all anymore. It is seeing interstellar space particles that are just kind of floating around in interstellar space. So Voyager 1 and 2 are the very first objects made by man that have ever left the influence or the area controlled and dominated by our sun. And you guys might have heard they both carry a gold plaque out into space that's got whale songs and drawings of humans and some information that was put together by international scientists and engraved on these gold plates and sent out into space that who knows, maybe someday might get picked up by someone else out there and they would learn about us. But they're still, Voyager 2 is pretty much, that mission is done because it doesn't have enough energy to keep sending information back to us. But Voyager 1, which again launched in the 70s, more than 40 years later, is still sending information back to us here on Earth. And it is giving us information that we are learning about the chemistry of interstellar space. And it is just mind blowing information that we are learning so much. And it's really changing the models of how solar systems like ours and the ones that we now know exist around other stars, how they float through space and what's in the space that's in between the stars. So we've gotten a lot of fantastic information from the Voyagers as we have from all those other NASA missions and the ones that are planned that maybe some of the kids on this call you grow up, you want to become an engineer or an astronaut or a space scientist. You'll be getting information from new missions that we're only now beginning to even think about what information as we learn from these missions that we've had in the last 50 years. And now we're learning information that goes into planning new missions that you might help plan and engineer in the future. So, Richard, tell us about what you've put up now.
So, I just want to mention there's quite a bit of resources that NASA offers at the nasa.gov website. There's resources that we offer at the scienceheads.org website. I didn't list here the JPL website. Once a year, in years past, not this year because of the health situation, but in years past, JPL has an open house once a year that doesn't cost anything. People can go and visit and tour JPL. They can see a life-size model of the Voyager spacecraft and see that record that Michal was talking about. That it was Carl Sagan who headed up that committee of scientists who decided what would be engraved on that record. They can actually see that, as well as many of the other space probes that NASA has sent into space. The SLU telescope that we're controlling, you can learn about that at slu.com. And the K-STARS planetarium software that we played with for a few moments, I've given you the link for that as well. Now, don't worry about writing this all down. I'm going to post this on our website along with a video of this presentation. I want to thank everybody for helping out tonight. Thank you, Michal, and thank you, Ruth. The information you provided was extremely valuable. I want to thank our guests for joining us, and want to remind you that we've got another online star party scheduled for July 31st. If you haven't registered for that, please go to the scienceheads.org website. And besides our online star parties, you can also schedule a free 30-minute personalized chat with a solar system ambassador. You can learn more about the other programs that Science Heads does and supports. And I think we're going to wrap it up. I want to thank you all. Thank you for joining us tonight.